Okay, it's 10. We can start. Nobody's waiting outside. So I will introduce you to George. I will introduce George. Drettakis. So he's a research director at INRIA in Sophia Antipolis. He defended his PhD in 1994 at University of Toronto with Eugene Hume. Then he did a year of postdoc in Grenoble with François-Xavier Sillon at INRIA. Then he got researcher position, then research director year 2 in 2003, year 1 in 2008. So he was leading the REV team that became Graph Deco, with now the current team at INRIA. He has had numerous projects, like big European projects like OpenFET, H2020, Marie Curie Fellowship, and now like a big ERC grant. So he has many projects and is working on like everything that touches rendering. So he makes us realize how wide rendering is, which is like he started with traditional global illumination stuff, and then he was everything about rendering. So it's real-time rendering, perceptual rendering, audio-visual rendering, now image-based rendering. So everything about rendering.
Neural rendering.
And neural rendering. So welcome, George.
Thank you. Thanks very much, Nicola. Thanks for the kind introduction, although I would prefer that we don't give the dates of my PhD anymore. So I'm going to do this in English. Mainly because I have never given the talk in French, and if I was going to do that, I'd have to practice all the terms because I don't know the terms in French. But of course, I'm happy to take. Je prends les questions en français sans problème à la fin, donc y a pas de problème. Okay, so today I'm going to be talking about learning in graphics, rendering 3D geometry, and synthetic training data. So neural rendering is something you've probably all heard about. And there are amazing results that generate extremely convincing images. So, again, and basically, you can see here, these are images that okay, bad start. These are images that are basically generated by a generative adversarial network, which takes a random number and generates an image. So when you see these images, when you show these images to anybody who isn't in graphics or vision, they believe they're photographs. It's very hard to distinguish them from photographs. And obviously, when all this domain started, I was going, why on earth would you want to generate an image from a random number? Why is that interesting? Well, what you can do is that you can then take any image and a real image and basically project it and find the random code that, well, no longer random, the code that corresponds, and you can get an image which looks very similar. And this, if you take it on generated images, it's almost perfect. But even for real images, you get to the point where we're capable of generating something that looks very close to the real thing. If you look from far away from where you're sitting, they probably look perfect. If you look closely, they're not, but still, we've come a long, long way. So basically, the point I'm trying to make is that these methods are now, it's hard to talk with the mask, they are now capable of generating very realistic images. That being said, at least for now, these methods have shown their capabilities for relatively constrained data sets. So typically it's faces. So faces is the thing that everybody cares about. Cats, dogs, cars, and churches seem to be the preferred domains that work well. And at least in the original, I'm going to have to slow down, right, with the mask. I can't use my normal speed. Originally, there was a huge number of images required for training. That's no longer true now, right? This domain is evolving a lot, so you don't need that many. So the question is, how can we control these beasts? So the problem is that, as I said, that these generators are just a random number that will give you a perfectly good image. Here, this is work by Toralba's group at MIT, where he's tried to analyze the network and find a piece of the neural network that controls, for example, doors or domes or trees. And that has been quite successful, but it's still something which is in process of being done. And this is typically called disentanglement. So if you think of a neural network as this big black box, everything is entangled, and you try to disentangle the pieces to control the specific parts of the process. So these things have amazing potential, clearly, right? I think when we look at these images, they're really great. However, if you look at the original work, it came from a 2D perspective. Most of the people who worked in this domain came from computer vision, and they basically usually ignored everything that we know about image synthesis. More recently, so I'll be talking a little bit about the NERF revolution. There has been a focus on 3D, but it still tends to ignore a lot of the computer graphics knowledge that we have accumulated over the years. So in this talk, our starting point is a computer graphics perspective. And basically, the idea is to remember that images are basically geometry, materials, and lights, and they have been generated by a light transport simulation. So, and what I'm going to try and demonstrate with the examples that I'll show is that 50 years of research have created many good, very good explicit models and answer the question, can we use neural rendering and physically based rendering hand in hand? So neural graphics is an exploding domain. If you follow arXiv, which my students do, there are new papers, many new papers, literally every day on this. Most of the work originally was object rendering, so taking a very large number of photographs of single objects, and then doing, so this is basically small baseline. When I say small baseline, the distance between cameras is small, often with multi-plane images, which are just images in planes which are parallel. And there was a lot of focus on human faces. As I was mentioning this morning, I gave this same talk in September. And I said, oh, it's going to be ready. I don't have to change it. And I looked at my slides and I spent 3 hours updating them because things have changed a lot since September, unfortunately or fortunately. So even though there is, it still remains specific capture conditions. So typically most of the papers we see take a dome around part of the scene. There is now some recent work on full scenes, which has been recently appearing on arXiv. And the small baseline is still the case. And also people tend to concentrate on very specific viewpoints. So if you look at the papers in neural rendering and NERF, it's typically just going around in circles close to the input cameras. So in recent work, there has been a lot of work in neural rendering for image transformation, so going from one image to the other, and these unsupervised generative methods. And there's sort of this antagonism between the two. So some methods basically start with something simple and try and transform it into something better. And then there's these methods like GANs, which are completely unsupervised. And then there's a category which try to learn a representation. So basically, these two examples, the science distance functions, and I guess James talked about these maybe yesterday quite a bit. And the neural radiance fields, these NERFs, are the idea that you take images all around the object and then you can render them. And NERF allows you to do things like this, where you can basically, as I said, they're not huge camera motion, but you get very good parallax. And the most important thing is that they can treat cases that are very difficult, like transparency, thin objects, and so on. Not perfectly, but it's getting better and better. And there's other work. So this was 2020, right? And since 2020, I think there have been literally hundreds of papers on this topic. There are other people who work in this domain. So Riegler and Colton had 2 papers that work on mesh-based approaches. So here they use a base mesh from multi-view stereo, which is similar to what we will be doing. And they learn features to allow, they basically merge features on the mesh to allow rendering in free-viewpoint. It's not perfect, but it is competitive and it allows much larger motion. The mesh allows you to move around much more. So just a small disclaimer about the NeRF revolution. So just in the last 2 weeks, there were over 20 papers that appeared on arXiv in this domain. Many of these things are amazing results, right? It's a constantly moving target. So what I'm going to show today should be considered as a sample in a design space. So there's a design space which is huge and is getting bigger. And what we've been doing is one example of how things can be done. Things move very quickly, and time will tell which directions have long-term promise. So compared to all this previous work, our goals are true free viewpoints in the sense of computer graphics, right? You capture a scene and you want to be able to move around in it freely as if you had a real model with lights and materials and geometry. And the other thing which I forgot to put on the slide is we focused a lot on interactive rendering, which is not the case in most of the other groups. We're one of the few groups that actually focuses on interactivity. We're interested in wide baseline, so taking a few photographs. Casual capture, I say casual in quotation marks, because it still requires a lot of photographs. You still need to take quite a few photographs to get a good result, but at least you don't need special equipment and you don't need to take the pictures in a very, very constrained manner. And until recently, we've been working a lot on full scenes, and I put an asterisk because in this talk, it's 2 out of 3 projects for full scenes. We did a small diversion into face rendering, as you will see. The reason we did that is that we're interested in working with generative models. And as I mentioned a few slides back, generative models only work on small classes of scenes and in particular faces. So we weren't interested in faces per se. We were interested in doing 3D, but the only set at the time we started the project, which was 2 years ago, the only class of objects for which we could work with are faces. Right? So just a very, very quick overview. This is stuff you all know very well, but I think it's important to ground what we're doing in the way we view graphics and this whole domain. So obviously, rendering, we want to generate images like the one we see here. We start with geometry that is modeled by hand or captured. Then materials are assigned to the different parts of the geometry. Lights are defined. And then we do lighting simulation to get the 3D rendering that we have. Obviously, we all know the rendering equation. The goal is to compute the radiance that we see from a given point towards the eye. And the key elements that we have are the materials. So they can be rough and glossy, which is a more complex behavior that we'll see in the last projects I'll present is an important aspect, or they can be diffuse, which is easier to model. We need to integrate light from all the directions, which is something which is very non-local. So if you're doing things exclusively in image space, you have to work out a way to deal with this. And obviously visibility is a key aspect that we'll see intervenes even in the cases when we're dealing with images. And then solving the equation, you need to do some very complex integration, typically using Monte Carlo. And the observation here is that this is again very non-local and requires a lot of computation. But if we look at the real world, photographs already have solved the complex rendering equation and give us the solution for free. So this brings me to the way we see the continuum from physically based to image based and now to neural rendering. So in image synthesis, we can see things as defining a virtual scene, defining a virtual camera, and then generating an image. And we can see computer vision as being the inverse. We have a real scene, we estimate the real cameras, and then we can get a camera poses and approximate geometry as output. So if we put these two things together, we get this continuum, and this is the way I see computer graphics today. It's this continuous domain where we can have a real scene, get the real cameras. If we could construct an ideal virtual scene, we could directly combine it with synthetic scenes, and then we can do virtual cameras and computer graphics in the standard manner. Obviously, there's a small problem here that computer vision doesn't give us an ideal perfect geometry, and it doesn't often give us any materials for that matter, and lighting is difficult to estimate. So image-based rendering was the first domain I worked on for a while. And the idea here is that you have the real input cameras, you have the approximate geometry, and to correct the problems of the approximate geometry, you use information that you project from the input images into the novel virtual camera. And this allows you to then blend the input images, but they're reprojected in the novel view. So it's important to remember this idea of reprojection, because we'll be using it very often to get the result. And if we look at the different aspects, so these are basically two different views of the world, which I think we can see as one. Traditional 3D rendering has the advantage that it's very flexible. We can modify everything. We have full control. Image-based rendering is hard to modify any content, geometry and lighting and so on, and we'll even viewpoint, and we'll see that how we address these problems in the rest of the talk. Light transport is expensive, however, so this is one of the problems of the traditional approach, which image-based rendering solves because the lighting transport has been computed already. And then the last point, and this is probably the point that makes it most attractive, content creation is very hard. If you're doing synthetic scenes, an artist has to work for many, many hours to create the geometry, define the materials, make the materials look like we want them to look like, define the lighting, work with the lighting algorithms to get the result. While for image-based rendering, captured content is instant. You just take photographs or video and you have your result. And what we'll see today is that neural rendering can bridge the gap between the two and allow us to get much easier and better results. And just to give you an idea for going from image-based rendering to neural rendering, the idea is that instead of actually explicitly using geometry, we will have a neural representation, so a neural network or neural networks, and we'll train this neural network using the input cameras as input. And then during rendering or inference in neural network terminology, we'll be able to generate the image by querying the network in one way or another. And just to give you a preview, this is older work, which I won't talk about. This is just a standard image-based rendering. So this was 27 photographs in a street in Nice, and we can move around with relatively good quality. And this is what I mean by true free viewpoint and wide baseline. And this was one of the first papers that used deep learning to improve the process by learning the blending weights. So it was a very simple idea. We just learned the blending weights, but learning the blending weights really improved quality. So there are three main principles in what we've been doing. The first is to use geometry as much as possible. Geometry is important because it gives cues or information to the neural network. Then we use rendering to help learning, but we also use learning to help rendering or to do rendering. And finally, we use synthetic training data when we need to disentangle difficult problems, and most notably in the case of materials and lighting. So when you have an image, materials and lighting are all mixed together. So it's very hard to distinguish what is due to the material and what is due to the lighting. And synthetic training data can help us a lot, and we'll see that in the last project. So the critical issues are how to provide this 3D geometry, how much rendering and how accurate do we have to do it, and is there a problem of domain transfer synthetic training data, which we'll see in the last project. So the three examples, the first one is point-based rendering that uses geometry and uses learning for rendering. The second project is this space-based freestyle GAN project, which uses also geometry and learning, but also uses rendering to help in learning. And finally, relighting indoor scenes that also uses synthetic data. These are the people who did all the real work. So my PhD students, postdocs, and collaborators and engineers. And this is work done by my European Research Council ERC grant FunGraph, which you can see there. So the first project I'm going to work on, present, okay, I'm like super late. Okay, I'm going to go a little faster, is point-based neural rendering with purview optimization. So again, the idea is this is a scene. These are the images that we captured. And our goal is to get high quality rendering, even from views that are far away from the capture. So we start with multi-view stereo geometry. So this is a computer vision technique. It's standard these days. And then if we use that geometry and just reproject the images, we get many artifacts because we see that the geometry isn't perfect and we get all these blurring and ghosting artifacts. So the question is, how do we deal with this? The first question we ask is, which scene representation do we want to use? So we can use meshes, we can use voxels, we can use points, which are a way to represent the geometry without having the connectivity of the triangles, or we can use these implicit representations such as NERF. In this project, we made the choice to go with points based on a mesh. So we start with the mesh. This initializes the point cloud, and then we will refine the point cloud using a neural approach. So why did we choose points? Are they good? Well, point rendering is something that is well known in computer graphics. So basically, they're fully integrated with the traditional pipeline. They enable differentiability, and they allow optimization of various scene parameters. And we'll see what those are in the following. And in particular, we use them in a per view setting. So concretely, what does this mean? If we have a novel view and these input views, what we'll do is we'll convert, we'll project the mesh into each view and then sample points on each pixel, for example. Then we can reproject onto the multi-view stereo geometry and from then move to the novel view. So we have this double projection that we need to do. And we choose only certain views that are suitable for this novel view. Then we have these rasterized point clouds for each input view. We use a neural network to generate the final image. So we see here that we've been using the geometry because we use the geometry to do the reprojection for the first part of this algorithm. We then do an optimization where we optimize different features. So for example, the depth of the points, but also the radius of the points that we're going to use for rendering, and a set of additional features that are critical in the quality. So I won't go into the details of the method. In all steps, we basically select input cameras. So we use a very simple maximum coverage solution to choose which cameras cover the novel view in a maximum manner, and we use those. Then we rasterize the point cloud. So in traditional rasterization, we have basically hard, each point will be rasterized in a manner which is, has hard borders. We use a differentiable rasterization. We didn't invent this, right? We just use techniques that have been developed by others, and we augmented them to take into account of the fact that we need to go from the input view to the geometry, and then from the geometry to the novel view, which is a simple addition to the traditional method. And importantly, we developed a layered rasterization approach, which is interactive in OpenGL. And this is thanks to the fact that points are completely integrated into the OpenGL pipeline, and they're well supported. And yes, it's possible to write CUDA kernels for everything these days, which is the big fashion, but these are just standard, right? So you don't actually have to do a huge amount of work to get it to work. So the differentiable rasterization of an input view will look like something like this. And the problem is that we need to combine several views and decide depth. So for a given novel view, this is an input view 1, input view 2, input view 3. Remember, these have been reprojected into the new view that we're looking at. And this is what you get. And you basically need to decide to give a weight on each view based on the depth to get the final result that you see on the right. If we don't do anything, we have problems with transparency. and we have problems with tearing. And without going into the details of exactly how we do it, we use a probabilistic depth test, which you can read in the paper to find out the details, which allows us to come up with a solution which is of much better quality. Then we need to optimize the purview information. So here you'll see what's happening. This will happen again, is we're seeing a visualization of the features during the optimization. So it'll look back in the beginning, there's not much texture. As it progresses, as the optimization progresses, you get more texture and sharper features. The way this happens is that we augment red, green, blue with 6 additional feature channels so that the network has more capacity to be able to learn what it needs to refine. And then we also refine depth, normals, and uncertainty. And these make a difference, which is kind of hard to see. But if you take out one of these, this is what we did here. We only use features, only use neural rendering, only no depth and normal and uncertainty. Uncertainty is the radius. Each one of them will create some artifacts here. There's some artifacts here. Here, the background is going to be blurry and so on. But when you put them all together, we get the best result. So the optimization is per scene. We take these input images, and we get a result in 6 to 10 hours for a scene where NERF requires 48 hours of training for the same machine. And the final component is neural rendering. So we have the colors, which are reprojected. We have the features, and then we use a neural encoder. We do for each view, we pull the weights, and then we have a neural decoder to get the final image. And this is the example where we see that the rendering in the end is actually done by the neural network. And this is where we see the second case of learning used for rendering. So the results are pretty good in terms of quality. The thing which is particularly important is the quality of at least we're very proud of the quality of the vegetation. So getting very high quality and sharp vegetation. This is mainly due to the extra features and the optimization of the features. But every other aspect helps a little bit compared to the deep blending approach. And even compared to NERF, NERF is very good, but it's still quite blurry in the features of the vegetation. When you talk to the NERF people, they tell you, yeah, but if you let it train for 3 weeks, it'll get better. But that's kind of the point as well, right? And we're better in the numerical comparisons as well, which these days you can't avoid. They're not very meaningful, but they are important. So to summarize this part, the point-based scene representation allowed us to refine these input per view parameters, and we have better quality at lower training costs. However, it would be nice to avoid the mesh-based initialization. And papers that came out last week show that this is probably possible. There are 2 papers on voxel-based representations, which could be used as an initialization for our approach, and is something that we'll obviously be looking at. The per view aspect adds one level of complexity to the algorithm, and hopefully we'll be able to get rid of that. And there's a standard problem for all image-based methods. What happens when you want to go to part of the scene which was not seen in any of the input images? For these, a generative approach is probably something that could solve it, and this is something we're also looking at. Which brings me to the next project, which is the first project in which I got involved in with generative adversarial networks, these GANs. And Thomas actually presented it, he had the discussion at 1:30 a.m. yesterday for SIGGRAPH Asia. I wasn't brave enough to stay up for that. I have to ask him how it went. And basically, as I mentioned before, we worked with StyleGAN2, which is able to create these images. So StyleGAN was developed by Teo Karas and the other guys in Finland. And StyleGAN2 is an improvement to this with various technical aspects. So this is all very well, but if we want to use these images and insert them into a 3D scene, how are we going to do this? That's the question. And there's a missing link, which is how do you go from the 2D space to the 3D space? And one of the ways to do this is by adding a camera and a camera space, which the generative adversarial network can recognize and it can use to generate images from a given viewpoint. So if I say, I want to insert this face onto this guy here, and I want to look at it from that viewpoint, you need to have a way for the GAN to understand the cameras. So there has been some work. So this is work by Ayush Tewari. The reference disappeared. So they're able to do very small motion, but they're missing a full camera description. And there's very limited viewpoints. So this is something which is a reality of the way StyleGAN 2 works. So StyleGAN 2 generates this kind of image. Notice what happens. The eyes and the mouth are always in exactly the same position when they come out of this generator. So this, again, from 1 month to the other, this changes. StyleGAN 3, the new version, can overcome this limitation, but it still is important for training. So this is sort of a side effect of the way that the data set was created. So GANs work at a very high level. The idea is that you collect a set of images that you consider to be a distribution. And then the generator will generate new samples from the same distribution. So what they do is they just take images from Flickr or these high quality images that look like this. And what they do is they use standard algorithms of face anchors, and they align them to be in a canonical position. This allows the network to solve a more constrained problem, right? It always needs to produce a specific kind of image, so it's easier. And GANs, which are based on these discriminators, which are hard to train, work much better in this case. So basically, this was our first observation for this project, because we want to do the 3D case, is that face pose variation is actually severely constrained. So our goal is to move to 3D. To move to 3D, we need to have 3D. So we do a rather specific case where we start with multi-view data, as we did in the previous project, and calibration and reconstruction. So the input to our method is 10 to 25 pictures of people who are, these pictures were taken by people who are not part of the project. So we just gave them instructions, and it's a casual sequence of capture. You need to have a plain background behind. Then we use multi-view stereo, and we get a mesh. And basically we apply the alignment, the standard alignment that we have before. What we're going to do is we're going to define a coordinate system with theta phi, which are similar to what I showed before for moving around the head, and d, which you can see as the vertigo effect focal plane control. So this defines a camera manifold, and we start with the dataset alignment, and we define the coordinate system with x left and x right, which we then extend to have x minus and x plus in this crop window, allowing us to base our coordinate system on this. And this will define the part of the space of 3D cameras that the StyleGAN can actually generate, because as we saw, it can only generate these restricted images. So we wanted to define quantitatively what are the 3D cameras that correspond to this space. And we use this 2D to 3D alignment process where we have our 3D model, which we reconstructed using multi-view stereo. And we use, again, these facial landmark properties to align the camera based on the landmarks. And this allows us to define a full 3D camera where we have 3D position, 3D rotation, and field of view. In previous methods, the 3D position and the field of view are not well defined. So if you don't have those components, you do not have a full camera, and you cannot insert the result in a 3D scene. And this is the first case where we're able to do this. And this shows how this method uses geometry. In at least one instance, it will use it again for the process of solving the problem at hand. So the camera manifold of the 7-degree space is actually very large, but Stalgan can only generate a small, the camera space is very large, and the camera manifold is this 3D manifold in this 7D parameter space. And this is what we identified. And we use that to solve an optimization problem that will allow you, for a given set of images, to define the manifold in question. And once we've done that, we basically have a face. So this is a captured face. And we see the variation of theta phi and the variation of d, which is this zooming in effect that you get that allows full camera control. And we wanted, the first thing we wanted to ask was, what are the limits of this manifold? So what we did is we generated, using Stalgan and random codes, we generated 10,000 samples, and we saw that basically there's a concentration of samples in a certain part of space. And then just using, we extracted curves that define these two curves, which we fitted with polynomials that define the limits of the manifold. So given all these components, we start with a free viewpoint camera. We project it into a manifold camera so that we get the closest camera, which is on the manifold, to the free viewpoint. Then we use an implicit latent representation network that will use this information to generate the Stalgan codes for the output image. So this is the important part. The important part is, as I mentioned at the very beginning, Stalgan, standard Stalgan, can take a real image, project it into the latent space, and generate it. What we do here is that we inject explicitly the information about the 3D camera, and we use a specific training process based on the 3D to train this implicit latent network so that it will generate images that not only look like the input, but also are consistent in 3D space. So that's the key aspect of the approach. And to do this, we use several perceptual losses and identity preservation losses, which you can read about in the paper. They are important, right? You have to basically inject these different components to get a good result. And for the training data, we use a two-stage approach. So initially, we take the aligned input views, which give us a very sparse sampling of the manifold. And then we use image-based rendering, so standard unstructured lumograph actually, to generate different views to cover the space. And the problem is that there are all these artifacts, but we can estimate the confidence of the uncertainty very easily. And this allows us to perform robust training. And we see here that the rendering is a key aspect to the training or the learning part of the algorithm for the implicit network. And this is the second element that Stalgan uses. So to generate images on the manifold, we've done this training procedure using the multi-view images. This gives us this implicit latent representation that generates the latent codes, and we get consistent views in 3D for images that are on the manifold. But as I said in the beginning, our goal is to do true free viewpoint synthesis. So we need to, and this basically shows how the generator is the learning process that does the rendering. So this is the third element, the rendering for learning. Leaving the manifold, though, is what we really want to do. So the latent manipulations are not enough. So what we add is we add, using the mesh, so using the geometry again, we use optical flow to generate a warping field so that when we have the Stalgan generated image, we just warp it to the novel view. So this is an imperfect solution, but it works quite well. So we can see that here, whenever these things are not aligned, we're outside the manifold. And whenever we go outside of these lines or outside of the lines above, we're outside the manifold. And we're able to render views up to a certain extent. After a certain angle, we start seeing the artifacts of the mesh, but it does allow a relatively good approach. And again, this is a second use of the geometry for this solution. So the other aspect which is interesting with this work is that we can do optional semantic editing. So we don't do anything special here. We just use standard techniques, notably GAN space, which is a paper from last year. So this is a standard capability of recent GANs. You can change the lighting, you can change the facial expression, you can do many kinds of edits, which again are not perfect, but do allow you to have a large amount of control. And we can even combine with classical rendering. So here we've inserted the model, because we have the camera, it's just compositing, right? It's not anything fancy, but just with compositing, because the view is consistent, we can insert it into a 3D model and have full integration. So to wrap up this part, the free camera was the missing link between GANs and 3D computer graphics scenes. We were able to define this camera manifold for the in-domain rendering, and we used image-based rendering to leave the manifold. So in future work, one of the projects we're going to work on actually really this year is trying other classes. So notably, we want to try cars. Cars are interesting because they're much more complex. Well, they're less constrained than faces, right? They don't just have 2 eyes, a mouth, and an ear, but they are pretty standard, right? Most cars have 2 lights, 2 or 4 doors, windows in the same places, and so on. So the hope is that we'll be able to get similar results using this approach. Obviously, we want to formalize the way of doing lighting, compositing, and so on. And inevitably, maybe it's time to move to a more nerf-based approach for these, because they allow a full 3D solution. So this brings me to the third project, and I think I'm doing okay for the time, which is on the free viewpoint neural relighting of indoor scenes. So indoor scenes are very complex. We have occlusions and indirect light. We have very weird light sources, different kinds of light sources, and materials with very different properties. So because they're man-made, they can be shiny, they can be diffuse, and so on. And the problem we want to solve is to change the lighting in these scenes. So just as a small anecdote, I like showing this video from 1999, where we were trying to modify scenes. So we were adding a virtual scene into this old scene, and we could move the virtual scene around, and we were very proud that we could do it with 1 second update time. And you'll see that moving very slowly. And most importantly, we could add a virtual light. So here you would add a light, and we were able to modify the illumination in this real scene, which included a synthetic object. So it was possible to do this, but at the time, we had to manually reconstruct the geometry by clicking on points, and the optimization was extremely limited, right? We had a fixed viewpoint and only diffuse scenes. So we want, obviously today, we still have simplifying assumptions that the geometry, there's enough geometry data, there's enough data to create geometry using structure from motion and multi-view stereo. We assume that materials are diffuse and glossy, but not completely specular, so we don't treat mirrors. And we assume that the lighting is a sum of independent light sources. So the key ideas is that the multi-view stereo will give us geometry, which we've seen in all the other projects as well. And the difference in this project is about materials. When you observe a material from many different viewpoints, you have information about it. If the appearance doesn't change in the different viewpoints, it's diffuse. If the appearance changes, it's shiny. So this is a material that you can estimate from these observations. And also, it's a requirement of our approach is that we take pictures of the light sources so that we can place them in the environment, and automatically or semi-automatically. And also, the idea is that we're going to use the geometry, the lights, and these material estimations to do approximate physically based rendering. So the goal is to remove or add light sources. So this is the original lighting. And this is the picture we take of a scene. And this is the kind of result we can obtain by adding a new light source. We want to remove or cast shadows. Again, this is very dark, but this is what the original image looked like. So we have to cast a new shadow, but remove the other one as much as possible. And we want to be able to handle this glossy floor. Since it's glossy, it has a highlight that needs to be able to move correctly when we move around the viewpoint. So the high-level idea is that we have the input data, which is a set of multi-view images. That creates the geometry. Again, this is common to all three projects. And the user will specify new target, what we call target light conditions. So we reproject everything into a novel view. We have the source lighting information and the target lighting information. And the neural rendering will use all of this information to generate a new image at a novel viewpoint with potentially novel lighting. It doesn't have to be novel, but it can be. So the idea is that to create the output image, we'll use a neural network, which we represent as F, that takes the input views. As I said, this gives you information about the materials. There's a diffuse hypothesis, so we estimate the incoming irradiance and the outgoing and the target irradiance, sorry, the target changed irradiance. And we'll also work specifically on the view-dependent illumination, so the mirror reflections, which will guide the view-dependent appearance, so for shiny surfaces. So multi-view gives us the geometry that I'm showing here as an example. So typically these scenes required around 300 photographs to take an interior. I took 3 of them during lockdown last year. It's a pain, but it's doable. And this shows how geometry is going to be a central element for this method. And we can use this to estimate the incoming irradiance. So the idea is that you have the geometry, and then you can, at a given point, you can cast a ray and query the input image, which you assume to be the lighting that arrives at that point. And that allows you to generate an image. So this is an image of the approximate irradiance of the source initial lighting condition. Then, and you do this by doing a very simple Monte Carlo estimator. Then you can take the estimated incoming irradiance and you can divide the input image by that, and you get a very, very, very coarse version of albedo or reflectance. It's not accurate. It doesn't need to be accurate. It just needs to be basic, because then we can use that to estimate the target lighting by using a colored mesh. And we again estimate the target, or the new version of the lighting of the irradiance, and then we can use the estimated albedo to get the target lighting condition, and then we'll give that to the network. So this shows, and this is the most interesting for me case of using rendering, so physically based rendering, to guide a neural approach, because we're going to have the estimation of the input irradiance and the estimation of the target or changed irradiance, and give that to the network as information so that it can generate the new images. And this shows, as I said, the case of rendering for learning, because these rendered images, which use physically based properties, will help the network learn how to render. For the specular hypothesis, the idea, this is a very weird image when you look at it. This is an input view, it's a synthetic scene. If you assume that every single object was a mirror and you rendered the image, you get this. This is very strange, and it's hard to look at, but it's very important because we can use it in the same way. So the same high-level logic as we used for irradiance, we can use it for the specular case. We can have the source mirror image, the source and the mirror irradiance. We can create a mirror pseudo albedo in the same spirit. Then we have the added lighting, and we get the target and the light image that we want to have in the specular space. So basically, we're able to generate target specular images as if everything was a mirror. Everything isn't a mirror, but the goal is that we'll have highlights that will move. These will be given to the network, and the network will be able to infer, using all the other cues, how to move things around. And we'll see examples of that in what follows. So, and finally, as I said, multi-view information gives information about the materials. So this floor, by looking at it at different viewpoints, we can see that there are these highlights that move around. And this information will give to the network to give it cues about the nature of materials. So all of this is in input image space. So these correspond to the input views, but we need to generate a novel view. And to do that, we reproject, again, this is the reprojection process of the input into the novel. And we have two groups. This is the standard image-based rendering approach, where we try and choose the views that are closest so that we have the best quality in terms of pixel values and resolution. And the second group, where we take the brightest and the darkest for each pixel in the reprojected image, which gives the network information about which materials change a lot. And therefore, these are the materials that have glossy effects. So the full pipeline is complicated, and I won't go into the details. But at a high level, we have all these buffers, which we concatenate them. So in the end, there's something like 25 or 30 buffers into a neural renderer, a network that is able to generate the result. And this shows that we're able, again, to use a neural learning technique for the rendering step. A quick, so the final element, which I haven't talked about yet, is training. So we train, in this case, since we want to separate lighting from materials and diffuse from view dependent, it's very hard to do that by capturing real data. You could, but it would require a lab and it would be very complex. So instead, we just use synthetic data. So we render the diffuse component and the view dependent component separately using a path tracer. We use 15 scenes with 8 different lighting conditions each. And then, and this is one of the tricks which we used in a previous paper as well, this is the synthetic geometry, the original geometry. And using a very specific method, we can run the computer vision tool on the images to generate a reconstruction of the same scene. And as you can see, it's kind of like bumpy and not very good quality, but it's qualitatively similar to the reconstruction of real scenes. By using these two different geometries, the network learns that even though it's seeing renderings from the perfect geometry, it's going to receive this kind of geometry when we're doing it on real scenes, and it can fix some of the artifacts due to reconstruction. So this is the case of synthetic training data. And now for results. So this is my whole way using original lighting and changing lighting. Let me do that again quickly. So the original lighting is here. And then we added these two virtual lights and the third light from above. We can do novel view synthesis. So notice that we have this floor with the highlight moving around in a convincing manner. So this is the original lighting condition. And if we have a relit novel view, again, we see that it's consistent in terms of the type of material and the result. Again, this is another example of novel view synthesis and with a relighting that we can get. And this is, well, I'll show the interactive case afterwards. Compared to NERF, so this is a very early version of NERF. More recent versions do better. So what you'll notice, what's important to notice here is the fact that we have moving highlights which move in a convincing manner. They're not 100% accurate, but they do correspond more or less to the, they correspond more or less to what what should be happening, right? You can see the highlight on the floor and then on the. So interestingly, NERF also does highlights pretty well. And that's one of the things that we're looking into. NERF kind of cheats, but it does have a view-dependent component, and it compensates by creating fake geometry behind the floor, for example. So this works interactively. This is an interactive session. It's like around 5 frames per second in our non-optimized implementation. So here we're changing the lighting and we're moving around in our interactive viewer. So it does allow the ability to interact, which is not the case, for example, for NERF-like methods. So this is basically the first method for relighting of full scenes with free viewpoint capabilities. So interestingly, we made the choice of treating materials implicitly. We don't explicitly estimate BRDFs. We estimate behavior, and the network takes care of relighting. And obviously, we leverage physically based rendering to enable these proximate geometry. So in conclusion, in future work, and this is something that just got accepted conditionally yesterday, we've been using neural techniques to do pre-computed radiance transfer, and we can see that training a multi-layer perceptron to do pre-computed radiance transfer allows us to do interactive rendering at essentially the same quality as path tracing. So this is something that is going to be much more common, I think, in the future. And we have another project also submitted in this vein. So it's not just for captured scenes. It's turning out that the power of neural networks for rendering is something that applies even to traditional rendering, to the point where it's really questionable whether traditional techniques have a future. So there are many open problems. Obviously, the long-term goal is automatic capture of shape, materials, and lights, and also motion. And I think it's key to only represent and compute as much as necessary for the goal. And choosing between neural and traditional techniques, depending on the needs, is important. Some of the traditional techniques are still useful, right? So we should always remember that. As I talked about generative models quite a bit. So there's the open question of, does it generalize? Can we use generative models for everything? I don't know, maybe, maybe not. Can we easily control and disentangle? Again, these are open questions. And again, it's always important to ask the question, is it really worth it compared to traditional methods? I find it somewhat annoying that people just go and say, okay, it's neural, it must be good. It's neural because it's interesting, definitely, but I mean, it is worth asking, are there previous methods? And it's important to know about the previous methods. For representations, I've talked a little bit about volumetric, explicit, sign distance functions, points, meshes. What is best for what? These are open questions. And the other thing that I've been wondering is these neural representations make the distinction between geometry, animation, rendering, lighting very mixed up. Is it even relevant anymore, or are all these things going to be one big neural thing, right? So to conclude, hopefully I've convinced you that learning and rendering can work hand in hand. And personally, I've never been as excited as I am now about the field of computer graphics. I feel that things are evolving in a way which was never the case before. It's like we're doing things, the ability we have to change the way things are happening and get the better quality result was just never seen in my entire career. And my career, as Nicola pointed out, is pretty long, right? So it's something that is to keep in mind. And as I said, the key elements I showed were geometry, rendering for learning, learning for rendering, and synthetic training data. So thank you very much.
We'll take questions, but I will ask George to repeat the questions.
Okay, sure. En français aussi, hein.
Okay.
Oui, oui.
Oui, ce que vous avez présenté, le roller mirroring, ça marche avec les photos, mais est-ce que c'est avec par exemple, des dessins où il y a des on va dire de géométrie ou plusieurs points de vue, il y a un vu par exemple le plafonning qui va pas vraiment avoir la même taille, ça marche aussi ou ça casse tout
So the question is, je réponds en français. Bon, je réponds en français. Allez. Donc, si j'ai bien compris la question, c'est est-ce que ça marcherait aussi pour d'autres types d'entrées, comme par exemple les dessins? Oui, c'était ça la question. On n'a pas essayé. Nous, on se base sur la partie. Donc, il faut qu'il y ait quand même une géométrie sous-jacente, une géométrie 3D sous-jacente. Donc, bon, mon collègue Adrien Bousseau travaille justement sur ce sujet. Comment créer de la géométrie sous-jacente à partir de dessins. Donc, si on a cette brique aussi, donc la brique qui va de dessin à 3D, a priori, il n'y a pas de raison pour que ça ne marche pas. Donc, après, on n'a pas fait et cette brique est nécessaire. Donc, du coup, pour toutes les méthodes qu'on a fait, la 3D est centrale. Donc, si on n'a pas une 3D complète qui explique le processus qui a généré l'image, ces méthodes-là ne peuvent pas marcher. Ceci étant dit, dans d'autres domaines, pas les nôtres, il y a plein de gens qui travaillent sur le rendu neuronal pour les dessins spécifiquement, mais c'est des techniques différentes.
So I have a question from Eric Guérin. Thank you for the talk. When you use synthetic data to train the model, did you experience transfer learning issues?
So that was the point of the slides I showed, right? So actually, the short answer is much less than we expected. Right. So we expected it to be a big problem. And globally speaking, I mean, there are details, right? For example, it turns out that Monte Carlo noise is actually useful because it sort of corresponds to the kind of degradation you have. It's not exactly the same kind of noise, but it does help, right? The step of having the dual representation of perfect and degraded geometry was useful. So that helps quite a bit. Overall, networks are very good at compensating. So my experience is that if you can get the synthetic data, it works very well. The hard part is getting it. It's very hard to set up the synthetic, Joanna knows all about this, the synthetic data processes.
Did you have issues with the dynamic range of your images? Maybe for the last project, where there's a huge light in the room here?
So we used 14-bit RAW. So the new cameras all have 14-bit RAW. And the process of, you have to be very careful to maintain the dynamic range throughout the pipeline. So you need to, so we used the raw images, which are converted to EXR. We use those for the reconstruction so that we get the undistorted images from the multi-view stereo in high dynamic range, which is maintained throughout the pipeline. And then you have to be very careful that you're doing processing in linear space. You apply a different tone mapping during the learning, typically a log or the one that's used in noise to noise. But so it's very important. Dynamic range is very important. So the more you have, the better. And you have to be very careful that you're in the right space for the different operations you're doing.
14-bit is enough.
Enough. 14-bit gives the results you see, right? So yes, if we had more, it would be better. I mean, for outdoor scenes, you probably need more. But again, all of these things are potentially solvable just by the network learning to deal with them, right? So there's a paper, one of the 20 papers is, it's called Dark Nerf. Actually, there's two of them. There's one on HDR and one on Dark Nerf. So Dark Nerf uses nighttime images with high dynamic range, well, HDR, and it uses the same intuition as noise to noise, that when you have several noisy images together, so in this case, in a multi-view context, the noisy images have zero mean, right? So that they converge to the clean image. So you can get rid of noise and actually increase the information that's available. So it's a simple idea, but the results are great.
Thank you for inviting us in your home. And I have a question regarding the last project. When you relight the room, it looks unreal. We see that it's a synthetic image. What do you think is the missing item to make it more real? Something missing in your framework?
So the short answer is I don't know. But if I had to guess, I would say that the light source models we have are extremely simplistic. So the light sources we insert in the scenes are just diffuse balls or diffuse quads, right? And those don't exist, right? There is no such thing as a diffuse ball in a real scene. So you're used to seeing lights that have more complex emissive properties. So including a more complex model would be useful.
Because you can take a lamp.
Sure. I mean, we didn't do it.
Yeah.
I mean, I would be tempted to say it should probably work, but there's a caveat to that we do make approximations in the way that we do the irradiance estimation. So it may be that doesn't preserve the qualities of the light source enough, but until we try it, I don't know.
Maybe for now, you get information from the scene, but you don't manage to get enough information from the lamps.
Well, no, because these are new lamps, right? So the new
Yes.
lights are exclusively what the user gives as a target illumination.
Yes,
right?
but if you get a model of a lamp from another scene, for example.
No, we don't do that. These are all the new lights are manually inserted lights. So that's what I'm saying. The manually inserted lights are not very realistic. So if those were more realistic, maybe it would look more realistic. But that's a maybe. I don't know.
Yes. Okay.
So yeah, two more questions from the part. So Guillaume Bonneau is thanking you, of course, for the talk. And can you tell us what you think about broader audience technologies such as the deep learning supersampling from NVIDIA to increase knowledge? It is only image-based with some temporal filtering components, so does not use at all through geometry. Could your work be extended and could lead to general purpose 3D engine for video games, for example?
So that's a very good question. So the DLSS obviously is amazing, right? I mean, and essentially, I don't know the details, but from what I do know, it's based on supersampling technologies, and those are extremely efficient and very well understood. And basically, the idea is if you train it on enough scenes, nobody knows how long they train it for on what scenes, but it works very well, right? And then you can train it on scenes specifically, right? So for your game, you can retrain it if you want. So, I mean, yes, these are all related in many ways, right? So they're also related to all the denoising approaches, right? There's a whole slew of deep learning denoising approaches which are extremely effective. And we work, I had one of my students was an intern at NVIDIA, so we talked to the NVIDIA people a lot, and they keep on going, right? Oh, path tracing is solved. You just need like 4 to 8 samples per pixel, which we can do with our new RTX. And then the denoiser will solve everything. I'm not sure that's completely true, but it's true for a large set of scenes. So in terms of what's going to end up in the game engines soon, the answer is that, right? So ray tracing plus denoising. The neural stuff is trickier, right? Because it's a change in the model, the underlying model of the pipeline. So it requires some adaptation. I don't think anything that I presented today is going to find its way directly into the game pipeline, but it probably will inspire stuff which will lead to changes in the pipeline so that they can incorporate neural things. Companies are definitely thinking about it, right? I mean, NVIDIA, Adobe, all the others as Google and so on, everybody's thinking about how to integrate the neural rendering techniques into the pipeline. And there was a presentation 2 years ago, actually, or 3 years ago, so the last SIGGRAPH that was live, where the NVIDIA people were saying, we're basically looking at the pipeline, and each piece we can replace with a neural method which is more efficient, we do, right? And because of the new, I mean, I didn't talk about hardware, it's a different talk, but it's related. So the RTX hardware is extremely interesting because it has a common platform where you have the tensor cores and the ray tracing cores together, right? With very low latency and basically the ability to communicate. So that opens up possibilities which are not available before. And I think that's where things are going to go in the medium term.
So another question, if you can. So that's from Nicolas Melado, en français.
D'accord.
Il a posé en français. Merci pour la présentation. Tu as présenté des résultats exploitant des nuages de points dans leur pipeline. Le développement des techniques d'acquisition 3D entraîne une explosion de la quantité de nuages de points 3D et un besoin croissant d'analyse de traitement. Peut-on imaginer une convergence des outils et des modèles permettant de traiter les nuages de points à la fois pour des applications en géométrie et en rendu?
Bon, ça rejoint mon dernier point, hein, qui était dans les diapos à la fin. Pour moi, il y a convergence. Donc ça, c'est indiscutable. Je ne pense pas que c'est particulièrement les points en particulier, parce que comme je disais, je n'ai pas d'avis tranché du tout de quelle est la bonne représentation, si c'est des points, les maillages, les SDF, les MLP, enfin bref, il y a plusieurs représentations possibles. Mais par contre, l'idée que géométrie et rendu, la distinction entre géométrie et rendu va être beaucoup moins prononcée, je pense que c'est clair. Et les points, c'est un exemple. Mais, après l'acquisition, c'est vrai que l'acquisition, aujourd'hui, le LIDAR commence à être partout, et ça, c'est typiquement des points, mais personne ne dit qu'on ne va pas, à partir de maintenant, utiliser le LIDAR justement pour alimenter un MLP, quoi. Donc, du coup, à la fin, ça peut être un MLP, ça peut être autre chose, ça peut être les trucs de voxel qui viennent de sortir. Enfin, je ne sais pas. Et c'est quelque chose qui va tellement vite que j'ai l'impression qu'on a vraiment besoin de prendre du recul et passer un peu de temps à réfléchir quelle représentation est bonne pour quelle application, quel contexte.
Une petite question. Est-ce que dans le deuxième projet, est-ce que ça peut être vu comme un transformer network qui essaye de transformer du coup une entrée sur un modèle 3D?
Oula. Enfin, moi, je ne suis pas un expert de transformer, hein, donc, mais je pense qu'il y a quand même un sens spécifique de ce que c'est un transformer network, et je ne pense pas que c'est ça. Non, c'est
Transformer, c'est de l'attention.
Oui, c'est plutôt de l'attention.
Oui. Les réseaux transformers, c'est pas transformer, c'est de l'attention, c'est où tu mets de l'attention pour faire des décisions.
Oui, donc c'est pas vraiment.
C'est l'image de cette petite transformation.
Oui, mais ça, c'est plutôt de image to image. Oui. Oui, mais c'est pas vraiment. Enfin, l'aspect, ce qui est plus important, c'est le fait qu'on utilise l'information multipliée géométrie pour pouvoir générer des codes latents qui sont compatibles avec la 3D.
L'apprentissage, il est fait scène par scène. Tu es obligé de réentraîner pour, si tu as une pièce différente, tu es obligé de réentraîner le réseau.
Donc la question, c'est est-ce que l'entraînement est scène par scène et qu'il faut réentraîner le réseau? Pour le premier projet, oui. Pour le deuxième projet aussi. Pour le troisième, non. Le troisième, on entraîne sur les 15 scènes synthétiques et après, c'est bon pour toutes les scènes. Donc, ce n'est pas toujours le cas. Et d'ailleurs, ça, c'est… Enfin, Nerf, c'est clairement dans ces catégories-là. Hein. Donc, on entraîne pour une scène et d'ailleurs, c'est très cher. Et quand tu parles avec des mecs de Google, ils te disent « Ouais, mais j'utilise un TPU pendant 10 heures et c'est bon. » Donc, je dis « C'est quoi un TPU ?» 32 GPU. Donc, où j'utilise 3 TPU et je le fais très vite. Donc, c'est très lent. Mais, justement, les papiers de la semaine dernière, il y a Planoxels qui arrive à faire une qualité qui est meilleure que Nerf en 15 minutes. Donc, bon, si aujourd'hui, dans un an, ils sont allés de 48 heures à 15 minutes, on peut imaginer que d'ici l'année prochaine, ou même d'ici la prochaine deadline vision, ça va être temps réel. Et il y a des raisons pour croire ça. Hein. C'est pas, par exemple, les NVIDIA avaient un papier cet été où ils présentaient ce qu'ils appellent les Tiny CUDA kernels, qui sont des kernels qui sont alignés comme il faut avec les registres et les bornes mémoire dans les cartes graphiques pour que ça tienne exactement, etc. Et ils montraient que pour les MLP, qui sont quand même en pratique des petites transformations et de multiplication de matrices, si tu les codes avec ces trucs-là, tu peux avoir jusqu'à 100 fois d'accélération. Donc, c'est 100, mais dans certains cas, même 1000 fois si l'alignement de mémoire est bon. Donc, il y a des bonnes raisons de croire que tu peux, et le problème de Nerf, c'est ça, hein, c'est l'évaluation du MLP sur les rayons. Donc, si tu arrives à l'accélérer à 100 à 1000 fois, C'est très, enfin, il faut pas avoir ce que j'ai. Moi, mon conseil, c'est que tout ce qu'on croyait avant, il faut l'oublier. Hein. Et il faut vraiment regarder avec un œil ouvert et très inclusif de tout ce qui est proposé pour voir quelle est la bonne solution.
I have one very technical question about the first project.
Okay.
So the future work, you said that maybe it would be a nice idea to get rid of the mesh. And my question, why do you have a mesh in the first place? Because structure from motion or NVS can produce a point cloud. And then you could resample it because you're moving from mesh to point cloud, but building the mesh itself is very costly. Well, it can be costly. So why do you go through this mesh step to go back to the points?
Okay, there's multiple answers to that. So the first one is that the mesh generation is not the most expensive part, right? The most expensive part is the depth map estimation, right? So that's what takes the longest in that pipeline. So the mesh itself is kind of a detail, right? But the real answer is that we use per-view meshes. So we use the technique that we developed in deep blending to refine the meshes per view, where we combine the Delaunay mesh with the dense depth maps, which are extracted from col maps. So when you combine these two things, the dense depth maps have more detail per view, and the Delaunay has smoothed things out and filled in holes. So when you combine the two, you get a much higher quality per view mesh. But all of this is old news. We don't need it anymore, right? I mean, with the new techniques, the experiments we've run on optimizing a point cloud using these methods it's better quality than anything that was possible before. It's mind-boggling, actually.
I have a question about the output and maybe what's in the internal representation of the neural network. So actually, currently for the output, usually you have images and you want to produce images from images. But wouldn't it be interesting to get labels and semantics instead of the final results, such that you know that this is a car, this is rocky round, this is metallic, this is because we have rendering algorithms. So given someone who wants to render the scene, maybe it would be interesting to look at the semantics of the scene. And the neural networks with their projection, then deprojection, or depending on the architecture, maybe you can have information about the response of the different neurons, and knowing that this part of the image is activates this part of the neural network, and so this corresponds to an eye or this corresponds to something.
Right. So the question is whether instead of just rendering images, we can. I'm making it a short version, right? We can use it to render segmentation maps, or just to render. Is that more or less what the question is? Yeah. Semantics labels. So one of the 20 papers last week was a Google paper on segmentation for objects, right? So they do exactly that. And then there's Matthias Niesner in Munich, who has many papers on this topic. So it's an active area. It's not my area of research, so I don't know much about it, but I do know that it is a very active domain, and it uses, you're completely right in saying that many of the techniques that are used for rendering can be adapted to do segmentation. So now there are 3D segmentation techniques, actually, were extremely impressive, which are trained typically on synthetic data. So it's the similar idea. It's a disentanglement problem. You trained it on synthetic data to get perfect labels, and now they give perfect 3D segmentation, like chairs, tables, screens, whatever, right? Just you give it images.
So we will stop, George, and if you have further questions, we can take it offline.